project is automatic test case generation using probabilistic type inference in Python. Here's a table of contents. We have research problem, related work, genetic algorithms, which is we will implement MOSA, type inference, and evaluation. Research problem, structural test generation in Python. First of all, why Python? Python is one of the most used languages in the world. Python is a dynamically typed language which imposes an extra challenge on software testing. For automating the test case generation, we need to know the types of the arguments and the variables of the file we test via structural test generation. It maximizes the coverage, it is consistent, and it explores the new edge cases. Related work. Our project is heavily relies on the guess what? Test case generation for JavaScript with unsupervised probabilistic type inference paper. In the paper, the main model is shown below. We have a static analysis, then unsupervised static type inference, which gives us the probabilities of the yielded types, and which we incorporate these probabilities in our test case generation. Genetic algorithms in SBCT. At first, single target. In our case, the branch was considered as an optimization target in single objective case. Next, the whole suite test generation tried to aggregate each objective into a single objective. In our case, summing the all branch distances to one objective function. This helped to get rid of some of the reluctant statements. But aggregation was not a good way of solving a multi-objective problem. So later, the multi-objective and many-objective solutions were applied in the SBCT. Many-objective, not multi-objective. Many-objective optimization algorithms, compared to multi-objective counterpart, are designed to address an optimization task with sufficiently more objectives, like 20. Why many-objective? From assignment 2, we saw that there can be 10 or more branches even for a small function that we should generate a unit test. Branch coverage formulation for MOSA. Given a set of branches to be covered, our goal is to find a set of non-dominated test cases T that minimize the fitness functions for all branches in the set. Test case. According to EvaSuite, a test case is a sequence of statements where each statement belongs to one of 5 types: primitive, constructor, failed, method, and assignment. In our implementation, we will only consider unit test case generation, so we care only about function statements, whose counterpart is method statement, and a class structural testing. For a test case, we have the following examples. In a given file, if we have 2 functions, which are foo and bar, test case 1 consists of the 2 function calls to foo and 1 function called to bar, and test case 2 consists of the 2 function called to foo and 2 function called to bar. MOSA. Main difference between the MOSA and the NSGA2 that we covered in the class. First is preference sorting. First front in the preference sorting is a set of non-dominated test cases where each test case has minimum objective score for some uncovered target. Apparently, the first front of the preference sorting is a subset of the fast non-dominated sorting. By doing so, preference sorting imposes a more selection pressure, in other words, elitism, on the candidates. Archiving. Maintaining a second population is helpful for storing the best test cases that have been observed through training. There are several other techniques that also involve the archiving, but archiving showed the best performance amongst them. DynaMOSA. DynaMOSA is an improved version of the MOSA in the sense that it reduced the number of targets that are considered during the training loop. It's implemented in the original paper, but we decided to stick with the MOSA since it is easier to implement and it is the performance improvement only. In other words, the coverage remains still the same. Still performs same with MOSA at the worst case. Offspring generation. While talking about the genetic algorithms, crossover and mutation are the important problem-specific implementations that we should consider. For our crossover, we decided to use a single-point crossover and also the crossover function of arguments. And for mutation, we decided to stick with a uniform mutation, which is also implemented in the EvaSuite and the original paper. Uniform mutation is an insertion, deletion, and mutation of an argument of an existing statement. Fitness function. For fitness function of the integers, we use the regular fitness functions that are taught in the class. For strings, we use Loewenstein distance, which is a recursive function as shown in the image. For classes, We will recursively apply the fitness functions to each property and sum them. And this will be implemented.
So another part of our project includes inferring type for each variables in function. In dynamically typed languages like Python, interpreter determines the type of variable at runtime, and this flexibility comes with both advantages and challenges. One of the challenges is that potential for ambiguity when it comes to understanding the types of function arguments, which causes issues when generating test cases. To solve the problem, we use static analysis of the code, where we classify the whole code as elements and relations, then try to look for certain type properties in them. We assign score to each type with number of hints, type of relations in expressions the variable is involved in. We repeat it for every type in the implementation to find probability of given variable being certain type. This will help us reduce errors when assigning type to variable when we generate test cases. For our current progress, our team successfully implemented type inference system for Python, focusing on integers, strings, and lists. This system reads through abstract syntax trees and maps variables to expressions to establish type relationships. Variable evaluation is then performed to derive numeric hints assigning probabilities to each type. This enables dynamic type inference and provides probabilistic understanding of variable types. For our initial testing, we used recursive binary search function since it uses several type of hints for each types. This is the results we got, and as we can see from the results, it assigned the iterable equal probabilities of being integer and list, which is a logical conclusion. On the other hand, our search target doesn't have any preferred type, since our type of the search target can be any type for our search space.
Now I'll talk about evolution. So if you remember, we told you that we will be using real world projects and open source projects to test our project. But one of these kind of databases were BugZimpy. But upon inspecting the BugZimpy, we actually concluded that we will not have enough time to cover all kind of things that are in those projects, and actually most of the projects in that database actually include some kind of networking, so generating unit tests will not be suitable for that. So we decided to simplify our goal, and we currently have two goals at the mind. The first one is the datetime library from standard lib. We chose this because it includes a lot of integers, string manipulation, and objects upon them, like dates, date times, converting from string representation of date time to actual object, and so on and so forth. And the second one was some algorithms that are implemented in Python, such as like binary search, as previously mentioned, but some more complicated algorithms like graph algorithms and stuff. And our baseline in the evaluation is the Penguin, as we mentioned in the proposal, which is much more complicated than our project, and which covers much more things than our project. However, it doesn't use type inference, and it relies on the static type annotations. And we think of the metrics to be evaluated to be, first one is coverage, and second one is performance, which is how much time it takes to generate those test cases. And currently we have remaining work to do. The first one is the user-defined types, namely classes. We have to make type inference work for them, and also we have to generate test cases that includes such arguments. And also Siraj mentioned the type of statements that EvoSuite generates, such as assignment, method, fields, and stuff. And we also thought about implementing that, but we are not sure if we will be able to finish it or not. And that was it. Thank you for listening, and yeah.